Okay, so let's start. This is the last lecture, and I will complete our discussion on neutron scattering and critical phenomenon. Again, my name is Young Lee. I'm a professor in the Department of Physics at MIT. So here is the outline, rough outline, and the basic topic will be quantum critical phenomenon, as well as how neutrons can study these phenomenon. So I'll start with a brief introduction, and then examples from neutron scattering in the literature. First, talking about spin 1/2 square lattice materials, pure and doped. And we can see how quantum critical phase diagrams have been proposed to be relevant to the physics here, and then some experimental observations of a certain type of scaling called omega over t scaling, where omega is the frequency for and h bar omega is energy transfer of the neutron and t is temperature. Then we'll talk about heavy fermion systems where quantum critical points have been actively discussed. And then we'll talk about one-dimensional chain systems where they're the cleanest examples of quantum phase transitions from a theoretical point of view and have some very nice features. One thing I should mention about this topic is that it is a very current topic, so there are fewer firm conclusions that can be made here. But perhaps one firm conclusion that we can make is that neutron scattering is an excellent probe of this phenomenon. Okay, so what do we mean by quantum phase transitions? And we can contrast this with classical phase transitions, which I discussed last lecture. And in the classical phase transitions, for example, upon cooling a collection of interacting moments, if there's a ferromagnetic coupling, then at some temperature Tc, then you'll have a transition to an ordered state. And if you start from the ordered state at low temperature and start heating up, well, you can melt this ordered state at a temperature in which the thermal fluctuations are strong enough to disrupt the order. So that's what happens classically when you melt such a phase. In a quantum phase transition, the phase transitions between different states are driven by quantum fluctuations rather than thermal fluctuations. So that is maybe a kind of obvious difference. And let's delve into that a little bit more. So what we're going to talk about then are transitions between phases that are ground states. So these are phases at t equals 0. And then how do you drive these transitions? Well, you need to tune some external parameter, and that's typically done by, say, an applied field or applying pressure or doping. But again, we're not going to be changing temperature to affect these transitions because these are transitions between t equals 0 states. And here's a typical phase diagram that you encounter. So temperature is now on the y-axis, and a tuning parameter is on the x-axis. And that tuning parameter, for example, could be magnetic field or pressure. And this is an example from a heavy fermion system. So what happens is that at some low value of this parameter, let's say that you have anti-ferromagnetic order of some of the magnetic ions in this material, and let's just jump to a large value of this tuning parameter, the ordering disappears and you have a metallic state. So there's clearly some difference, a different phase from both sides, and at some point you will go through a critical point. And that's a critical point that exists at t equals 0. But what's interesting is that at higher temperatures, the critical fluctuations around that critical point become are very robust, and you can measure these fluctuations at high temperature. And in this phase diagram, it kind of forms this fan of critical fluctuations. And here I guess is a pictorial example of what could be happening in a heavy fermion system. And I'll say a few more words about this when we get to that topic. So that's one feature of quantum phase transitions. You have some parameter that you tune at t equals 0. A few more features, and there are different systems that one can draw such similar phase diagrams for. So you'll see this a lot. Again, this phase diagram where you have some parameter called g on this x-axis and then temperature on the y-axis. And you can go between states where in this case you have magnetic order with classical spin waves, and on this other side you have a disordered state, essentially with singlets, where the excitations are called triplets or triplons. And then in between, at t equals 0, there's a single critical point, but then you have this quantum critical region where the effects of that critical point will be strong. Something that's very interesting about quantum critical points is that you have very non-trivial quantum entanglement at that critical point for that ground state if you could sit right at that point. Another interesting aspect is that the relaxation time is given by the following expression. C is some universal constant that just depends on simple parameters of your system. And you have this h bar over kt, and this turns out to be the fastest possible relaxation allowed by quantum mechanics. So if you perturb the system from equilibrium, it relaxes back to equilibrium as fast as allowed. And a consequence of this feature of quantum critical behavior is that in a neutron scattering experiment, the intensity that you measure for excitations, and if you measure some excitation with energy h bar omega, that will only depend on the thermal energy kT. So we call this omega over t, or h bar omega divided by kT scaling. And that will be a feature that we'll see in some of the neutron measurements. All right, so let's start some case studies of various systems where you might think quantum phase transitions could be important. And you would want to study systems in which quantum fluctuations should be important. And we've already seen such a system before, and that's the spin 1/2 square lattice. And in fact, we had talked about the possibility, at least Anderson had put this forward in the early days of high temperature superconductivity, the notion that the ground state for spin 1/2 on a square lattice could be what's called the RVB, resonating valence bond state. So this is a state where all the spins pair up with another and form a singlet, and the wave function is some superposition of these singlets. This is a quantum disordered ground state. There are fluctuations due to the quantum mechanical nature of the spin 1/2, and this is in contrast to the more classically ordered state, the nil antiferromagnetic ground state. We do understand the square lattice a lot better now, but back then it wasn't clear where this stood, if you had nail order or if you had something more exotic. Just the early theory for this, or let's say in theory, the possibility existed that there was quantum disorder ground state in such a system. When people tried to prove that the system was ordered in the t equals 0 limit, it's possible to show that's true for large spin, for spin of 1 equal to 1 or larger, that there is going to be Néel order in the t equals 0 limit for a Heisenberg interaction. And I should remind you, this does not violate the Mermin-Wagner theorem, which says there cannot be a finite temperature phase transition for a continuous symmetry order parameter. This is going to be ordering in the t equals 0 limit, so not at finite temperature. However, it was hard to prove that the case for spin 1/2 orders on the square lattice. People had believed this to be true, but there was no analytic proof of this. Then there was some seminal work done by the people in the paper that I copy below, Chakravarty, Halperin, and Nelson. And what they did is they mapped the nearest neighbor Heisenberg model with spin 1/2 onto a continuum theory, so a continuum field theory called the quantum nonlinear sigma model. And from this, they extracted the low energy physics, so the long wavelength behavior. And they had a parameter in their theory, let me go to that next, which changed the quantumness, in a sense, of the system, and they had this parameter labeled G. So this phase diagram as a function of G on the y-axis, and then this is temperature on the x-axis. It's just like the two phase diagrams I had shown in previous slides, but it's just kind of rotated by 90 degrees. And what you see here is that there is a critical G value that separates two regimes. One they call renormalized classical, and it's classical because that's a state that has long-range order in the t equals 0 limit, and the higher G state is quantum disordered. And the basic observation then is that real materials that are good examples of the spin 1/2 square lattice, like lanthanum copper oxide, they do in fact have Bragg peaks at low temperature. And in fact, Professor Sinha first saw this with neutron scattering, that there was Bragg ordering in this spin 1/2 square lattice system. So that these systems should fall for this G value below 1, and then they would have a prediction based on their mapping to this field theory that the correlation length as a function of temperature has this exponential dependence. So this diverges exponentially as you approach t equals 0 with this specific way. And in the exponent, you have this rho sub s, which is the spin wave stiffness, and it's just related to J. So you should be able to compare experiments with theory with no adjustable parameters. So there were some neutron results very soon after. This is work by Keimer and co-workers. So this is the Bergeneau group at MIT. And they made large single crystals of lanthanum copper oxide. They paid careful attention to making sure the oxygen stoichiometry was right, because if the oxygen's slightly off, you actually dope carriers into your system. And they wanted to study the pure undoped square lattice for this set of measurements. And so here are some of the results. And what they did here, so this is just like the type of measurements done by Bergeneau and co-workers on K2NIF4, which I described in the last lecture, where they are scanning across the rod of 2D fluctuations. So this is above any ordered state. At the special Q, that gives you this efficient energy integration without varying the Q in the plane. And they measure this at various temperatures, so 500 Kelvin, 400 Kelvin, 325 Kelvin, and this is now right at the nail temperature. When they extract the correlation length from these fits, and they use a simple Ornstein-Zernicke Lorentzian fit, they get the following data points. So this is kappa, which is the width in Q, so this is the inverse correlation length. And they see that kappa starts to drop, meaning the correlations increase as you cool down. And clearly at Tn, they should go to 0, because that's where you have long-range order, and you should have your divergent correlation lengths right at that critical point. And you can then compare the temperature dependence with theory, and these are comparisons to the quantum nonlinear sigma model, which is in the renormalized classical regime. And there seems to be a pretty consistent fit overall of how the correlation length or inverse correlation length changes, as well as the intensity. So you can conclude that lanthanum copper oxide does fall in this renormalized classical regime, and this actually proves experimentally that the 2D square lattice does order in the t=0 limit. It turns out lanthanum copper oxide, and I actually mentioned this in the first lecture I gave, that was 3 lectures ago, has a certain number of spin anisotropy terms in the Hamiltonian, such as a Dalachinsky-Maria interaction. And that leads to some of the spin wave gaps that exist. Now, Dalachinsky-Maria actually promotes ordering. So there's actually a better square lattice system that doesn't have this Dalachinsky-Maria interaction because the copper-oxygen copper bonds are straight instead of buckled. And this is called strontium copper oxychloride. So this is probably as good a 2-dimensional spin 1/2 square lattice that you will find. It has very small XY-like anisotropy, and this is just the 3D coupling, which is very small. And so measurements were done also in the Bergeneau group by Grevin and coworkers. And here J is about 125 millivolts. So they measured with various incident energies because, again, you want to measure this S of Q static structure factor. So you need to integrate over all the relevant energies. So you want to go to high energy as well. So this is 41 millivolts. It's not as large as J, but that's okay as long as the energy scale for the fluctuations at these low temperatures are well integrated over the fluctuations that dominate. So here are some data from 500 down to, I guess, 390 Kelvin. And again, this is using this static, quasi-static approximation. So here are the results. This is now the correlation length divided by the lattice constant, and they measure up to, I guess, over 200 lattice constants with high energy resolution, and this is over a fairly wide temperature regime. And they can now apply this or try to fit this with some of the theories. I think there's some comparison to, again, the quantum nonlinear sigma model. It goes a little bit beyond the approximation that Chakravarty, Halper, Nelson had made, so this is even a more accurate prediction from theory that matches the data really well. And there's also comparison to quantum Monte Carlo for the Heisenberg model, and that also matches well. So it looks like the correlation length is very well understood, and it's again consistent with the fact that these real materials on the square lattice fall in this renormalized classical regime. And up to you can imagine now, if you believe this phase diagram, that if you go up to a high enough temperature, you will exit from this renormalized classical regime and enter some quantum critical regime. And that was also looked for in the data, but that was not seen. So all of the data points fall onto the renormalized classical prediction very well. So it looks like the effects of this quantum critical behavior are not seen in the undoped spin 1/2 square lattice. So, I mean, these are neutron measurements that show that quantum criticality is not important in this particular system. And you might say, oh, that's kind of disappointing, but it's actually very nice work that was a triumph of showing the match between theory and experiment. And it's not true that everything is lining up perfectly well. If you closely look at the peak intensity, so S of Q equals 0, and compare that to some theoretical predictions, there are deviations. So the theory in this case is the dashed line, and the data do not completely agree with that. So there's some discrepancy with the renormalized classical prediction. But again, the correlation length prediction is a more rigorous result. There were some additional assumptions made for the theory for the intensity. Okay, so that's the undoped system. Now what happens when you dope this spin 1/2 square lattice? And many of you know this is how you get a high temperature superconductor. So here's a phase diagram that many of you have seen before for, this is lanthanum copper oxide doped with strontium. And at very low doping, there's this narrow phase here, which is your 3D anti-ferromagnetic insulator. And then at some point at very low doping, it's roughly around 2% doping of holes into your system, that anti-ferromagnetism disappears and you enter what's called a spin glass regime. And you no longer have long-range spin correlations. And at some point where you dope above 5% holes, you enter into a superconducting regime. So you can ask, when you start doping, what happens to the correlation length in the fluctuations as a function of your doping level? And what happens to the dynamics, again, when you just start to destroy the anti-ferromagnetism? And these types of experiments have been done by Keimer et al., where they concentrate on very low doping levels. So these are not superconducting materials, but they're in the so-called spin glass regime. And the data that I showed you just a few slides ago for pure lanthanum copper oxide are these white, these circles. It's kind of hard to see here. Yeah, I think they're the white circles, and they're again shown here. And you see that this inverse correlation length goes to 0 at the nail temperature, because that's where you have long-range order. Once you start doping to levels that destroy the long-range anti-ferromagnet, you see something interesting in that the inverse correlation length now goes to some finite value. And that value becomes bigger as you increase the doping level. So if the inverse correlation length is finite, that also means the correlation length does not diverge to infinity, but it just goes to some finite value as well. So the correlation lengths are no longer divergent, even in the t equals 0 limit. So your ground state is a disordered ground state. There are questions about what type of disordered ground state it is. Further neutron scattering measurements were done on this to probe that. So again, these measurements that I'm showing on this slide were done in 2-axis mode to get S of Q with energy integration. You can then do inelastic measurements, and I'll show you those next, to get information on the spin dynamics. So this is in one of the same materials that were shown on the previous slide. This is with 4% strontium doping, so again in the spin glass regime. What you see, these are at fixed energy transfers, 4.5 here, 6 millivolts, 9 millivolts, and 12 millivolts. And when you scan at fixed energy, you see that you get a nice peak that is always centered at the same position for the different energies, and it's at this H of 1. It's the 100 position, which is sometimes referred to as the pi-pi position. It is the anti-ferromagnetic wave vector position. But these are not sharp Bragg peaks. You just have broad peaks centered there at various energy transfers. Here is the intensity at different energy transfers. This is integrated over the Brillouin zone, so it's taking the integrated intensity of the peaks that I showed you in the left figure and plotted as a function of temperature. Right. So you can see data at 2 millivolts, 3 millivolts, and over a wide range of energy transfers up to 45 millivolts. And you see that there is a temperature dependence to the intensity, and there's a very simple way to model that. And what they did to model the intensity is the following. So here, this is again the Q integrated imaginary susceptibility. So this can be extracted from S of Q and omega via the fluctuation dissipation theorem. And they fit this quantity to a form that obeys omega over t scaling. And it has this complicated, arctangent form. You don't have to worry too much about that. The main thing is that all of the data taken at different temperatures and different energy transfers collapse on the same line if you plot it as a function of omega over t. So that is showing some scaling. And it was a very significant result at the time. There were some theories particular to the Coop rates that had predicted this. But another thing to note is that this is also a prediction for being near a quantum critical point. It's not clear that it doesn't mean that this must be a quantum critical point, and it's not clear that that is the case, because there are other reasons that can give you this omega over t scaling. Some popular ideas were having a marginal Fermi liquid, for example, and others. Now, that was at very low doping in the spin glass regime. There's been work at higher doping levels, close to the optimal doping value for high temperature superconductivity. And this is work done by Apley and co-workers on 14% strontium doped lanthanum copper oxide. So there's a lot of background that goes into this. I don't want to go over all of the details, but there is one difference that you can readily see between the low doping and the more highly doped materials. It's that as a function of Q, so this is at some fixed energy transfer, in your scanning Q, you see that the peaks are no longer centered at 1, where the anti-ferromagnetic wave vector is, but you have 2 peaks split off symmetrically from that position. So these peaks are now incommensurate. So the superconducting state of lanthanum copper oxide has incommensurate spin fluctuations. What Apley and co-workers did is measure at various energy transfers in a wide range of temperatures the fluctuation spectrum of these incommensurate peaks. And they did some nice polarized work to confirm that what they're seeing is magnetic. And you can see that things sharpen up considerably going from high temperature, so this is close to room temperature, down to, and the print is kind of hard for me to see, but to much lower temperature you get much sharper peaks. So you can now plot the following. So this is the inverse correlation length, kappa again, and this is plotted as a function of temperature squared plus omega squared, all under a square root. And this is another way to show that you have omega over t scaling in this compound. So you see that all of these the fact that omega over t scaling may be because there's a quantum critical point nearby, and I think there's a lot more indicators that there is a quantum critical point near this doping level. Again, this is a very active field, and there are no firm conclusions to be made here. But I think there's definitely a camp of scientists who believe the quantum critical point in this near this doping level could be important to the physics that is observed. And neutron scattering is one of the principal evidences for this. Okay. So that was the copper oxide materials, the 2D square lattice, doped and undoped. Quantum criticality plays a bigger role, I would say, in other correlated electron systems, the heavy fermion systems being one of them. And there's a substantial history behind this. And I will skip a lot of things. And there's some very nice review papers, this being one of them, Heavy Fermions and Quantum Phase Transitions by C. and Steglich. So some things that are quite interesting in the heavy fermion systems is that in this particular compound, if you change this particular compound here, if you change the pressure, you can reduce the nail ordering temperature, and as you go to a high enough pressure, in the vicinity where this nail temperature disappears, that should be a quantum phase transition, you actually see a superconducting dome. This actually occurs in many systems, and this looks like some kind of general feature, that superconductivity often appears in the vicinity of the quantum critical point when you destroy some magnetic ordering. In this other compound here, this is a color contour plot of the exponent in the resistivity versus temperature. This red means that the exponent is close to 1, where the blue or purple is the exponent being close to 2. So an exponent of rho being varying as t squared makes a lot of sense for just electron-electron interactions in a Fermi liquid model. Having rho, the resistivity, go as just linear in T is very unusual. You cannot get that in Fermi liquid theory. This is called non-Fermi liquid behavior, and it appears that you often get non-Fermi liquid behavior in the vicinity of a quantum critical point in these heavy fermion compounds. What are some of the basic ingredients in these heavy fermions materials? What you have are some elements that have partially filled F electrons, and they are on a crystal lattice, and then they have conduction they're in a sea of conduction electrons. So what can happen is that there's a hybridization between the electrons on these F orbitals and the electrons in the conducting C, and you get some coupling, some condo entanglement of these electrons. So these F electron ions have a magnetic moment, but they can be screened by the conduction electrons if you have a strong enough hybridization. And this is related to the condo effect. So you can get a condo singlet-like ground state between the F electrons and the conduction electrons. Usually at low temperatures, you have an ordering of the moments on the F electron elements. If you change some parameter, you might be able to diminish to get rid of that ordering. And you can say that's a quantum critical point. There are different scenarios for how this can occur, and that's what's tried to be drawn in this cartoon. So you can have the condo singlet remaining intact in the ordered state or not. Right? In this picture up here, this is trying to show you a cartoon of these large black arrows are the F electron moments, and then the smaller red arrows are the moments in the conducting C, and they form these singlets. So this is your hybridized condo singlet C. When you have ordering in this other scenario, you break that singlet. So the F electron moments are now simply localized. You have well-defined local moments that form this up-down antiferromagnetism. And you don't have this screening of that moment due to the Kondo effect. All right, so how does this play out in a real material and in experiments? So here are some famous results by Schroeder and co-workers on this compound cerium copper gold. And this was a test of how does this transition occur between going from the unordered, just heavy fermion metal to the ordered antiferromagnetic state. And this occurs as a function of, like, in this case, doping. So by changing the amount of gold, you can change on this phase diagram where you are. If you just have the heavy fermion metal state to the magnetically ordered state. And there's a critical gold concentration in which this occurs, and they studied a compound right at that critical concentration and at this trajectory and temperature. So the question was, how does this transition occur? Is it the case that you have, in this upper picture, you always have this Kondo singlet screening of your F electrons? So these black arrows shown up here are your F electrons, and you can see that at low temperatures, they're no longer unscreened or free. But in contrast to down here, you see that you do have these well-defined local moments in this V-shaped region all the way down to the quantum critical point. And so in this case, you do have this quantum critical, very familiar to us by now, this V-shaped quantum critical phase diagram where you have some ordered state on one side, a different state on the other side, and some quantum critical regime in between. So they did measurements on these compounds, and they are measuring the F electron magnetism. And so here there are scans in Q at fixed energy transfer at different temperatures, and here's the intensity as a function of energy down here at different sets of Q. And again, there's a very nice way to summarize the data, and that's shown here. So here's a summary. So they are plotting for this top figure. This is the neutron scattering data, but they're plotting this as energy transfer divided by kT. So again, this is omega over T scaling. And here they have the intensity, and they're multiplying by temperature to some power. So they get some exponent that comes out of this scaling. So they see that now all of their data taken at different temperatures and energies fall onto the same curve. What's further interesting is that they measure the uniform susceptibility, say in a squid, and they can plot that uniform susceptibility at various fields, applied fields, at different temperatures. And if they do an H over T scaling, shown here, all of the data fall onto the same curve as well. And they're also taking the susceptibility times temperature to the same power that they're using above. So these are very different techniques. One is measuring the uniform susceptibility, one's measuring inelastic neutron scattering to get the local susceptibility, and they're seeing very similar scaling behavior. One reason that you can get this type of scaling behavior, again, is being in proximity to a quantum critical point, and I think that is probably a very good conclusion that can be made from their results. And there are other heavy fermion materials. This was measured even earlier than the work I just showed you by Aronson and co-workers on this uranium, copper, palladium material. Something that's kind of interesting is that if you just measure this is almost the raw neutron data. S of, I guess this is the intensity as a function of energy. I don't know if it's Q integrated or not. Yes. Okay. Well, what you see is that the structure factor itself looks very temperature independent. Right? So even at different temperatures, on the positive energy transfer side, there isn't very much difference. And that turns out to be characteristic of having omega over t scaling. So they can do a plot of omega over t, and then they extract the susceptibility times temperature to some power, and they also get this nice collapse of the data. And for these heavy fermion systems, there definitely is the conclusion to be made that you're close to a quantum critical point because you have this competition between magnetic ordering and just metallic behavior. But there's also some complications due to disorder, and sometimes impurities can give you scaling behavior. So I think that's still an issue that could be fleshed out better. Okay, so now let's turn our attention to one-dimensional systems. And one-dimensional systems are really textbook examples of quantum criticality. There's a textbook by Subir Sachdev called Quantum Phase Transitions, and they have many chapters on one-dimensional systems. And in particular, there's a very nice one shown here, and it's a ferromagnetic Ising chain. And you can add a transverse field. So here's the Hamiltonian. You want to have Ising moments, and J is positive to make this a ferromagnetic interaction. And then you want the ability to apply a field in the perpendicular direction to the easy axis. And that gives you a phase diagram as shown down here. So at low fields, so essentially at zero field, for example, you will have a ferromagnetically ordered chain at low temperatures. And then you can ask what type of excitations do you expect from such an ordered state? Well, once you flip, to create an excitation, you can flip all of the spins from one side of some domain wall compared to the other side. So there's no further energy cost for having all of these red spins down. It's just the energy cost at this domain wall between the red spins and the black spins. So if you have these domain walls in one dimension, and it's similar to the 1D spin 1/2 chains, where you break apart your spin wave into 2 spin 1/2 spin-ons, which act as domain walls, you can get continuum type of scattering. Now, what happens in high fields? Well, in high fields, again, this is in the direction perpendicular to the easy axis. You want to align all your directions, or all the moments in the direction of the field. And in that case, you need to have some superposition states of your up-down in order to get this effective moment direction along x. And then in this case, you can picture your excitations as having quasi-particles, single quasi-particles that flip from the field direction to the opposite direction. And then in between these two states, this will be an ordered state, this will not be an ordered state. You have this quantum critical point at some critical field. And there is a nice material, this cobalt niobium oxide compound, that has these zigzag spin chains of cobalt, which are the magnetic ion. And it's shown in this panel here that there is magnetic order at low temperatures. And by applying a transverse field, you start to diminish the magnetic order, and the ordering disappears above some critical field near 5.5 Tesla into some paramagnetic state. So this is work done by Koldea and co-workers. They studied the excitation spectrum, and as I mentioned before, this is a cartoon of the excitations in the ferromagnetically ordered state, where you create these domain walls between your upspins and your downspins, and these domain walls can propagate, and what that gives you in the excitation spectrum is continuum scattering, which is seen at these low field values to the left of the critical point. So that are these domain wall quasiparticles. Now, above the critical point, you're in this non-ordered state, this paramagnetic state, and then you just have these spin-flip quasiparticles, which are well-defined modes, and that's what you see in the spin excitation spectrum. Now, this is not a truly one-dimensional system, and nothing really is. You will always have some small couplings between the chains. So this is in zero field, so you're not in the quantum critical regime yet, but you're in the ordered state. So they did measurements at some high temperature, 5 Kelvin, and at much lower temperature, where the interchain energy becomes important. And what they see is that they break up the continuum scattering, shown on the left here, into well-defined modes, which appear because you now have bound states. And the bound states appear because you have coupling between your neighboring chains. And one way to think about this is this cartoon at the bottom, where you have two kinks on this very bottom chain, and if you have coupling to the chain next to it, well then, depending on how long this red segment of downspins is, you have unfavorable couplings with the neighboring chain. So the longer that red segment is, the larger the energy cost. So these domain walls can no longer propagate away from each other to infinity, because that will just cost too much energy, so they're bound. Another way to say that is that they're confined as well. And the fact that you have these bound states gives you these discrete spectrum in the excitations. Now, the interesting thing in this system was to measure near the quantum critical point. So he did experiments in magnetic fields close to this critical field and looked at how the excitations changed. And it turned out that, again, this is a 1D system where theory is much more readily doable. And there was some theoretical work long ago, I guess in the 80s, I believe, and even I think by a particle physicist, who showed that there's a hidden symmetry in this transverse field Ising model near the critical point, and you should get 8 sets of excitations in this vicinity, and there's something called an E8 group symmetry that emerges. And it's quite remarkable that the neutron experiments very nicely bear this out. So what they did is they measured 2 excitations labeled M1 and M2, M1 and M2 here, at different fields approaching the critical field. And there's a specific prediction in the theory in that the ratio of these 2 energies as you get to the quantum critical point should fall on the golden ratio, which is kind of a cool idea. And in fact, the neutron results bear this out. If you plot the ratio as you get closer and closer to the critical field, this is approaching this golden ratio. And this bears out this very interesting prediction from long ago. And this is definitely affects being in the vicinity of a quantum critical point. Okay. And another example for a one-dimensional system that, again, is one that is more theoretically tractable is having dimers. So you have a quantum dimer model. Here's the spin Hamiltonian, where you have pairs of spins that are coupled together in a dimer. And so the low temperature, low field phase is going to be shown here in this phase diagram. You have a quantum disordered state, so there is no magnetic ordering because you essentially have singlets on these dimers. So you have gaps to your excitations. And if you apply a large enough field, well, you go from this gapped state to a state where you now have magnetic order at high enough field. Oh, I'm sorry, I guess you can change pressure. I mean, you can change some parameter where you get rid of this gapped dimer state to having some ordered state. And then you have gapless spin waves in that ordered state. And then in between, you have this quantum critical point with these regime of quantum critical fluctuations. So what they can do in this compound, thallium copper chloride, is apply pressure to affect this quantum phase transition. So by applying pressure, you can measure the intensity of some Bragg peak. It's 0 in the quantum disordered state, and then it starts to rise in a continuous manner. And something that I should have pointed out long ago is that we'll be just looking at quantum phase transitions that occur in a continuous manner rather than first order phase transitions where you don't have this extended critical regime. Okay. So something that was very interesting here is that in the low field phase, that's where you do have these singlets, and the excitation should be triplets. That's very expected, and you should have transverse and longitudinal components to these triplet excitations. And they measure those and they label them on the left set of figures. You have L for the longitudinal mode and T2 for one of the transverse modes. And you see that as you increase pressure, the energies of these modes starts to diminish. And that's what should be happening because at the quantum critical point, the gap should close. Now what's interesting is now for these right plots, C and D, these are at pressures above the critical pressure. So now you're in this magnetically ordered state where you expect to have your spin waves. And you normally expect there to be this gapless spin wave. This is your Goldstone boson, and that's this T1 that they try to point out here. But they do have some spin anisotropy, which can give you a gap, which is T2, as you shown here. And you see that this T2 does not change with going to higher pressure, but they have this other feature, which they call the longitudinal mode, which changes with pressure. And at higher pressure, away from the quantum critical point, the intensity diminishes. But just the fact that you have a longitudinal mode in an ordered state is unusual. Because recall, if you just had regular spin waves, you only have transverse excitations. Right? So the fact that there's a longitudinal mode in this ordered state can only be explained by the fact that you're in proximity to this quantum critical point. So that's very interesting. And they can now summarize a lot of their observations on a phase diagram. So on this diagram to the left, they're showing as a function of pressure how the energies of the different modes change. So on this quantum disordered side, you see that the modes diminish all the way to 0 at the quantum critical point. And then on this ordered side, you should see some transverse spin wave modes that are essentially 0, the Goldstone bosons. And then you see transverse mode T2, which is pretty flat at some energy due to spin anisotropy. And then you see this longitudinal mode here that changes in energy with pressure. And that's the kind of novel feature here. you can look at this longitudinal mode. For example, here's the intensity in figure C here, and the intensity seems to definitely respond to the quantum critical point, almost divergent-like. And the width in energy as well is shown in panel D here. The width of this longitudinal mode gets sharper and sharper as you decrease the energy. So it looks like it's, a well-defined quasi-particle should have a very narrow width in energy to have a very long lifetime, and this does in fact seem to have a very long lifetime close to the quantum critical point. So this longitudinal mode in the renormalized classical phase has a very narrow width in energy, and it looks like that's a well-defined quasi-particle, which is an interesting observation. Okay, I'm even earlier than normal this time. So that was kind of a whirlwind tour of various ways neutron scattering has made an impact in studying quantum critical phenomenon. So I think it's clear from last lecture and this lecture that neutron scattering is an indispensable probe of both classical and quantum critical behavior. I would argue it's one of the most important probes, and it's very versatile as well if you have the right samples. And quantum phase transitions and quantum criticality are very modern, cutting edge topics in condensed matter physics, and magnetism, in particular quantum magnets, are central players in this important field of study. If you study magnets with neutron scattering, there's a lot of really interesting research for you to do. Okay, so that is it. Are there any questions? All right. Well, thank you all. And that will be it for today.